Hey everyone, welcome. I'm speaking to you today on behalf of Forge College, and I am absolutely thrilled to dive into this explainer with you. So if you've been following along with our Programming with Solana track, specifically the Interacting with Solana Clients and Programs module, you already know we've been gathering our parts and mapping out the terrain. Like in our previous lesson, we went over the theoretical patterns for a client interaction setup, really breaking down the philosophies of how apps should talk to the blockchain. But today we're putting on our safety goggles, we're transitioning from theory to physical assembly with our introduction to Rust client development. Think of today as laying the absolute bedrock for every single thing your decentralized application is ever going to do.
All right, so here's our agenda for today's assembly. We're going to meet the Rust skeleton, gather our blueprints and dependencies, securely configure our keys, test for a pulse, and then finalize your client assembly workflow. Let's get right into it.
First up, Section 1, Meet the Rust skeleton.
You know, every brilliant engineer dreams of building this heavily armored, unstoppable transaction-sending machine right out of the gate. But we've got to be disciplined here. Before we bolt on the heavy armor of complex smart contract interactions and token transfers, we absolutely must construct a stable, perfectly balanced skeleton. And that's exactly what a Rust client is. It's a program that assembles, inspects, and submits transactions to a Solana cluster while also managing account serialization. Basically, it's the bridge. The Solana cluster is out there, right? It's processing thousands of transactions a second, and your Rust client is your personal envoy to that cluster. It holds your configuration, it precisely formats your instructions exactly how the on-chain programs expect them, and it handles all the complex cryptography of signing those requests. Without this client, your app is totally isolated, but with it, you're directly plugged into the global state of the network.
Okay, moving on to Section 2, Blueprints and Dependencies.
Look, you wouldn't try to build a fusion reactor by just throwing random metal into a pile and hoping it works, right? No way. You need precise raw materials and the exact right tools. In the Rest ecosystem, those tools and materials are our creates. If we look at our cargo.toml manifest, getting this skeleton standing requires a few specific dependencies. First, solana-client. This is the heavy lifter that actually handles the network communication and the RPcClient. Next up is solana-sdk. This gives us the foundational types, things like keypair, pub key, and the core cryptographic signatures. These two are totally non-negotiable. But what's also really essential to mention are the optional crates, DIRs and anyhow. I highly, highly recommend them. The DIRs crate is incredibly helpful for dynamically finding a user's home directory across different operating systems, so you can reliably locate keypair files. And anyhow? Well, that makes error handling during your early development phase an absolute breeze instead of a massive headache.
Which brings us to Section 3, Configuration and Keys.
Now, this is where things can get a little dangerous. We're essentially wiring the power supply here. And I've seen way too many novice engineers accidentally blow up their projects, or honestly, much worse, their wallets, because they got sloppy right here in this phase. So we have the bad way and the good way. The bad way is hard coding your local key paths and cluster endpoints directly into your source code. Look, if you hard-code your private key path, or heaven forbid, the private key itself, and you push that up to GitHub, well, congratulations. You've just made an involuntary, highly efficient donation to an automated hacker bot. Not to mention, if you hard-code your RPC URL, your client completely breaks the second you want to switch from devnet to mainnet. So, what's the good way, the engineered way? It's using std.env.var. By reading Solana RPC URL and Solana keypair from your environment variables, your client instantly becomes portable, reproducible, and secure. If the environment variable isn't there, your code can gracefully fall back to a default devnet URL. This is literally the hallmark of professional engineering. Keep your secrets out of your code.
All right, so you've gathered your dependencies, you've wired your environment variables perfectly, and your code compiles. The physical assembly is done. But how do we actually know our skeleton is alive? Does it breathe? Let's find out in Section 4, Testing for a Pulse. We aren't going to ask our skeleton to sprint a marathon just yet. We're not building or signing any mutating transactions today. Instead, we're just going to use safe, read-only methods to check its nervous system and look for a twitch. The absolute core of this system is the RpcClient. This is your main entry point. It's your primary communication wire to the blockchain. When you initialize RpcClient.new with your URL, it configures everything you need to handle synchronous JSON RPC requests to the Solana cluster. It manages the HTTP request wrapping, the JSON serialization, the response parsing, the whole shebang. You instantiate this once, and then you reuse it to send and receive all your vital signals. So, what specific signals are we sending?
we're doing 2 pulse checks. First, we call getLatestBlockhash. This is a fantastic network test. It's essentially asking the cluster, hey, what time is it over there? If you get a hash back, it means your network routing, your RPC URL, and your client dependencies are all functioning perfectly. Second, we fetch an account balance using getBalance, passing in the public key we derived from our loaded keypair. This checks the network, sure, but it also proves that our keypair file was successfully located, read, and parsed by the SDK. So that's 2 simple read-only calls. There's 0 risk to your state, but they absolutely validate the entire foundational plumbing of your application.
Now, something to keep in mind, when you call get_balance, the cluster doesn't return whole Solana tokens. It returns lamp ports. That's the smallest fractional unit of Sol, named after the brilliant computer scientist Leslie Lamport. Just to put that into perspective, 1 Sol is equal to 1 billion lamp ports. And honestly, here's my absolute favorite part of this whole exercise. When you print that balance out to your terminal, you might literally see 0 lamp ports returned. And you know what? As an engineer, seeing 0 lamp ports is actually a massive victory. Why? Because it proves your code executed perfectly, it talked to the blockchain, it parsed the response, and it didn't crash. It just means your devnet wallet needs an airdrop, which, hey, that's a problem for the Solana CLI, not your Rust code.
Let's wrap this up with Section 5, your client assembly workflow.
We've gone over the parts, the safety protocols, and the testing. Now let's condense all of this into a standardized operating procedure, something you can put right into your engineering manual and repeat every single time you start a new Web3 project. This table is an architectural map that explicitly connects our concepts to the exact Rust modules you'll be writing. For your RPC connection, you're going to reach for solana_client_RPcClient_RPcClient to handle those synchronous cluster requests. For keypair loading, pull in solana_sdk_signature_read keypair file. This is beautiful because it seamlessly reads the exact same JSON keypair files generated by your Solana command line interface. For your environment, use std_environment_var for that safe, reproducible configuration we talked about earlier. And finally, for your read-only RPC checks, you utilize methods like get_balance to validate connectivity safely. Definitely keep this schematic handy. It's going to be your cheat sheet.
And here's the physical process, laid out in 4 foolproof steps. Step 1. Create your crate with cargo new and add those dependencies to your manifest. Step 2. Configure your runtime settings. Get those environment variables set up on your machine. Step 3. Implement your read-only operations. Write the actual code to instantiate the client and fetch that block hash. And step 4. Cargo build and cargo run. If you follow these 4 steps, you will have performed a complete minimal hygiene check on your development environment. You're basically ensuring your tools are razor sharp before you start carving the masterpiece.
And if everything goes according to plan, you'll look at your terminal and realize the skeleton is breathing, the plumbing works, the network is responding. This is a fantastic milestone. So, on behalf of Forge College, I just want to commend you for your rigorous attention to engineering fundamentals today. We've successfully isolated and solved dependency management, RPC connection, and safe keypair handling. I highly encourage you to visit forge.college to dive even deeper into this track and explore a wealth of other Web3 engineering topics.
But before we officially wrap up this explainer, I want to leave you with one final thought. Your skeleton is built, it's wired up, it's breathing, and it's just waiting for your input. So, what instructions will you command it to execute next? Because in our next lesson, we're going to start bolting on the armor, attaching accounts, and writing the mutating transactions that will actually alter the state of the Solana blockchain. Until then, keep your wrenches handy and happy building.